Yeah, great people. How are you guys doing today? Welcome back to some Economics YouTube channel. Yeah, so optimal control theory. At last, finally, almighty OCT. Here we are today. All right, so optimal control theory OCT. So abbreviation for it. So optimal control theory seeks to select a stream of values over time for the control variable that will optimize the functional subject to the constraint set on the state variable. I know this might just look like jargon to you, like what is control variable, what is functional. Okay, you already did calculus of variation, so you know what functional is. But then what is state variable, and so on and so forth. So there's an example on the board. So while solving a question, I would explain all of these things to you. So in this particular case, here 4x minus 5y squared is the functional. Okay, so that is what you are trying to maximize. So OCT seeks to select a stream of values over time for control. So t is time. Okay, for control variable. So what is the control variable? The control variable is y. Okay, so which is here yt. The control variable because its value selected or controlled to optimize j. J is what you call the functional, like what is inside here. So you use j to represent the functional. Then xt here, this is the state variable. It's a variable in motion. Okay, I guess because of the dots s that is on it, whatever is a variable in motion. Then you also have lambda t. So lambda t is similar to the Lagrange multiplier as it estimates the marginal value or the shadow price of the associated state variable. Now, from your budget constraint, now let me first explain what a control variable is. In a research, a control variable is a variable that is constant, that is not allowed to change. Okay, so let's say, for example, what's your love of banana supply again? An increase in price leads to a reduction in quantity demanded. Other things equal. So those other things equal, right? Like the consumer's income, like the taste of the consumer, like the culture of the consumer. Those ones are the control variables. You understand? So they do not change. You don't allow them to change. So as you are carrying out your research, you include some of these variables to make your work, kind of exhaustive. Kind of um, what are these can I use now? So you kind of it is there to make your work oh, I don't know the English. Just kind of it's there to make your work broad, something like that. So you don't just say you're conducting a research on the effect of price on quantity demanded of, let's say, chocolate or pizza, and that's just it. No. So in an econometric research or an economic research, you need to add other control variables to allow your work to be kind of broad. So this is your main thing that you're looking at, the effect of price on quantity demanded of pizza. But then for your work to be broad, you need to include other factors that might also be influencing quantity demanded apart from price. Okay, so maybe three or four of those other factors. So to make your work kind of broad rather. So those are the control variables. They are not allowed to change. All right, so I've explained that. Now, so lambda I was talking about your budget constraints. So usually you would have an objective function, which is a utility function for consumer behavior that you want to maximize. So let's say the utility function is u equals xy. All right, for two goods with x and y. Oh no, let me use x1, x2. There might be an alpha and there might be a beta here. So a Douglas function. Then you have a budget constraints, the income of the consumer, which is equal to price of x1 times x1, then price of x2 times x2. So when you're setting up your function in a Lagrangian form. So u as a function of x1, x2, and this one is going to give you x1 alpha, x2 beta plus lambda into bracket y minus p1 x1 minus p2 x2. All right, so for those of you that have gone through these classes, uh, before you start to do something like optimal control theory, anyway, you must have done a lot of Douglas and so on and so forth. So here now, you then continue to maximize, the process of maximizing your utility function, getting your x1, your x2, you know, and so on and so forth. So now, if you look at it, you are going to get the value of x1, x2, and lambda. So the value of lambda here, whatever you get as your value of lambda, is telling you that if your income, Okay, which is the constant of your constraint. So this is your budget constraint. You understand? So the income here is called the constant of the budget constraint. So it's telling you that if the constant of the budget constraint should increase by just 1 unit. Let's say it increased from 19 to 20. Your utility, your total utility, the value for your utility here is going to change, like it's going to increase by the value of your lambda. So that's like the effect, that's like the work the lambda is doing. So if the constant of the constraint should increase by 1 unit, just 1 unit, the total utility will change from its original value and increase by the value of whatever lambda that you've been able to get. So like the kind of that kind of thing is applicable here because at the end of the day, while trying to solve this, we are going to set up the Hamiltonian, and that is actually something like in the lambda form. Okay, so I just kind of went into this to explain what this lambda might be doing over here. So here it is similar to Lagrangian multiplier, and I've told you the work of Lagrangian multiplier as it estimates the marginal value. So that's what this guy is kind of trying to do here. Marginal value, that is when the constant of your constraint changes by 1. You know, when you do things like that, I'm talking about marginal utility, when total utility increases by 1, right? Marginal whatever, um, marginal product, when your total product change in TP as a result of changing, you know, quantity, okay, of labor or whatever input is used, marginal product of labor, change in total product as a result of a change in, you know, quantity of labor used, and so on and so forth. So here, lambda is also telling you the change in u that's going to happen when y changes by 1 unit. Change in u that will happen when y changes by 1 unit. So what is that change is what this lambda is going to be equal to. So let's say your lambda is 20, all right. So and this was 19, and this is 200. So what it's telling you is that if 19 rises to 20, right? No, okay, no, let me use that. Let's say this was 14. So if 14 rises to 15, right? The total utility that was 200 before we increase to 20. Remember the value of lambda is 20, so it increases to 20. So it increased by 20. If it falls, the same thing. All right, if this should fall from 14 to 13, okay, I used 14 the other time, right? From 14 to 13, total utility that was 200 before will fall to 180, that it will fall by the value of the lambda. So it's talking about the marginal. So the same thing here. So it's similar to the Lagrangian multiplier. It estimates the marginal value or the shadow price of the associated, state variable. So marginal value of this guy. All right, we kind of memorize it, but at least you know the what the lambda is doing. So how do we solve this? Okay, before that, we have necessary conditions for maximization. There's also sufficient condition, which is very similar, the same thing, not even very similar, which is the same thing as what we did. So thank God. Somebody saying thank God, yeah, that's good. You don't have to cram a new thing. Okay, the same thing with what we did when we are looking at calculus of duration, and same as the Asian. So first thing is the h, the y, because where the h come from is when you set up your Hamiltonian. So that's the first thing you do. The h, the y equals 0. So then the next one is the lambda, the t. Not that it is lambda per se, but it is written as, the stuff is written as this, something like this. But it's just easier for me to write it like a profit, like as if it's a profit. Okay, so the lambda, the t equals to. So when you do the lambda, the t, what you are going to get is this x dot, the state variable x dot. So you might, use this to get this, or you might use this to get this. Anyhow, now for b, the x, the t, no, 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 minus the h, the x. No, 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 I'm gonna miss it. So this is lambda minus the h, the x will give you lambda. Then there, the x, the t equals state variable x dot n. You can use this to get this. So then the third condition, x0 equals x naught, xt equals, when we start solving, you know what I mean. Now the first two conditions are known as the maximum principle. So you might have a question that says use the maximum principle to find out the state variable, the control variable, and the co-state variable, whatever. And the third is called the boundary condition. So the two equations of motion in the second condition, okay, equations of motion, x dot, like it is moving, x dot is moving, lambda dot they are moving, they're in motion. Okay, of motion, I call the Hamiltonian system or the canonical system. So I've written these things out in case you have, maybe you're writing an exam and then there are some objective questions that require you, or let me say some fill in the gap questions that require you to like, you know, provide these answers. All right, but I know that's not really your business. Business is how do I just solve this problem on the board. So here, like I said, you set up this is the function. So you set up the Hamiltonian. So Hamiltonian h as a function of I just want to write it in a very proper format, not that I can't solve it. Um, okay, so there's that. H not as a function of anything equals with this function now 4x minus 5y squared, but now it will be plus lambda into the state variable, all right, xy. All right, so from here we are going to do three things: the h dy, so the h dy so equals 0. All right, so the h dy is where is y? Y is there. We have minus 10y, right, plus 8 lambda equals 0. So from here, y equals to minus 8 lambda over minus 10, which is 0.8 lambda. So you cannot believe that. Let me call this guy equation 1 to make things easy for this guy equation 2. Alright, so we are done. Now remember, this is for lambda. Lambda is there's going to be a minus in front, minus the Hamiltonian dh dx dot. That is for it to get lambda minus, what have I written? Dh dx dot? No, dh dx. Alright, so for it to get this guy, so you could use this formula or this formula. So minus dh, so since the subject here is h, it's kind of easier now. Minus dh dx. Minus is in front. So minus dh dx is equal to minus, anyway. So what's dh dx? And this minus is the minus here. Dh dx is 4. Okay, so this is equal to your lambda dot. Lambda dot is 4. This guy. Then for you to get x, x is so I can call this one equation 3, right? So you have the h, the lambda equals, there's no minus for this. Now the h, the lambda is there equals 8y, equation 4. So what we do is that okay, which is, wait, before I write that, which is equal to x dot, so equation 4. Right. So what we are going to do is um we express 8 lambda 8 x dot in form of this. So since y equals 0.8 lambda, so x this is equal to 8 into brackets y is 0.8 lambda here, 0.8 lambda, which is equal to 6.4 lambda. So equation 5, keep that somewhere. Okay, so now we deal with lambda dots. What we are interested in doing is to first we deal with the lambda. I want to get lambda out. So lambda equals to integral lambda dot dt, okay, from calculus operation class. That's not difficult to get. So equals to integral of minus, what is lambda dot? This is lambda dot. So minus 4 dt. So we have minus 40 plus c1, which is equation 6. So we substitute equation 6 in equation 5. This is equation 5, the states state variable equation. So here x dot equals 6.4 into brackets. There's lambda. Where is it? It's bracket lambda. So and this is lambda now. So substitute here. This multiplied by this is minus 25.6 plus. All right. So the thing is that we want to get x, not x dot. So for us to do that, so x is equal to integral x dot dt, which is integral minus 25.60 plus 6.4 c1, so dt 6.4 C1 this. All right. So x will be equal to minus 25.6 t squared over 2. I'm not supposed to be writing like this, but some students can be very, very funny. 6.4 C1t plus C2. Yes, since this is x3 plus 2, 2. So x equals to 25.6. Is that not 12.8 minus 12.8 t squared plus 6.4 c1t plus c2. Now let me check. Minus 12.8. Okay, okay, okay. So this is, we are getting closer to getting our state, variable. But how do we get C1 and C2? So recall, that's why I didn't clean this. Recall that we're giving x naught as 2, x3 as 117.2. So this now, because what we actually have here is xt, and write it like that, xt. So x naught will be equal to minus 12.80 squared plus 6.4 c10 plus c2 equals 2. All of this becomes 0, so c2 is equal to 2. Right? Now, when time is 3, so x3 equals minus 12.83 squared plus 6.4 3 c1 plus c2 is 2 equals what is here? 117.2. So x3 equals minus 12.8 times this is 9, minus 12.8 times 9 minus 115.2, then plus 6.4, 6 times 3, 18, 0.4 times. So like 19.2 or thereabouts, plus 19.2 C1 plus 2 equals 117.2. Alright, so 19.2 C1 equals 117.2 minus 117.2 plus 117.2 plus 115.2, then minus 2. Okay, so 19.2 C1 equals to 230.4. 230.4. So C1 equals, when you divide to C1 is 12. So your state variable in full, xt, is equal to, we go back here, we have minus 12.8 t squared plus 6.4 C1 into bracket 12 t plus C2, 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 C2. So 2 plus 2. So xt equals minus 12.8 t squared plus 6.4 multiplied by 12, 76.8, 76.8 t plus 2. So this is the state variable. So this is our state variable. So next we either look for our co-state variable or our control variable anymore. So let's look for co-state variable. So lambda t. So lambda t or something, you remember, that was minus 40 plus c1, minus 40 plus c1. So c1 now is 12. So this is equal to minus 40 plus 12. So this is our co-state variable. And what's our control variable, which is yt? So yt equals to, I think it was expressed as lambda somewhere. Yeah, yt is equal to 0.8 lambda. So we have 0.8 lambda equals to, and since this is lambda t, so you have 0.8 into bracket 4 minus 40 plus 12. So this should be minus 3.2 t plus 80% of 12. It's 9.6. Okay, 9.6. So control variable is that. So So these are control variable. So next is to test for sufficiency condition. Alright, sufficiency condition. And actually, we can evaluate the value of y as t equals 0 and t equals 3. Alright, so since this is y, when t equals 0 and t equals 3, as the original question, for the original question, we had the upper bound was 3 and the lower bound was 0. Alright, so we can just decide to, so when t equals 3, so y into bracket 3 equals to minus 3.2 bracket 3 plus 9.6. Our answer here is 0. Now for y 0, when t is 0, so you have minus 3.2 into bracket 0 plus 9.6 equals 9.6. So we've evaluated at the upper bound and the lower bound. Okay, so lower bound being 0, upper bound being 3. So what we can conclude from here is that the optimal time part of the control variable is linear. Starting at 0. So let me just write that out. And in fact, if you were asked that what is the slope of the control variable, what would you say? What is the slope of the control variable? Now, if you recall from your linear algebra, maybe your secondary school, your high school, whatever. So when you're writing out something, when you're writing out a line, like this, the equation of a line, so y equals mx plus c. Where this is a constant, this is the slope. Now, when we use that for this, okay, it's synonymous to y equals minus 3.2t plus 9.6. So the constant is 9.6 and the independent variable here is x, but what we are using for our own is time t. M is slope and slope here is minus 3.2. So m equals minus 3.2, which is the slope. Alright, the slope is minus 3.2. So I was just saying that from what we've done, so you don't need this for us to get the slope. Just from the control variable equation, you can get the slope. Now, can we also get the slope from here? No, we can't get the slope from here because this is a quadratic function. Okay, we also have the slope of the constant variable is minus 4. Okay, so minus 4t plus 12. So minus 4 is m, t x is t is x, whatever. 12 is a constant. So it depends on the question that you're asked. So from here, what can we conclude? We say that the optimal parts of the control variable, the optimal parts of the control variable is linear starting from, so now mention these values starting from 0 and 9.6 and ending at 3 0 with a slope of, what was our slope? Minus 3.2 of minus 3.2. All right. So why do we say that it is linear? This is a linear equation. The highest power of the independent variable is raised to power 1. The independent variable is time. This is not linear. This is a non-linear equation because the highest power here is 2. This has become a quadratic function, but this is a linear function. So like the optimal time part of our control variable here is linear. And where is it starting from? It's starting from when we substitute to this y3. If you look at the question was for you to maximize 3 knots, 30, then where is it again? 30 4x minus 5y squared dt. So that's why I use 30 here. 30. So it's starting from, it's the optimal time part is linear. is starting from after you put in the value of 3 and 0 into the time part of the control variable, because 0 and 9.6, it's starting from 0 and 9.6 and it is ending as 3, 0. Alright, when you substitute the value of 3 into the optimal time part, what did you get? 0. So it's starting from 0, and when you substitute this into the optimal time part, you get 9.6. So 0, 9.8, and it is ending at 3 and 0. So that's it. So the next thing we've done all of this, the next thing is to find the sufficient conditions. And I told you that it's similar to what we did in the previous class on calculus of erosion. So we apply that same matrix. So we'll be needing the discriminant tests, page 2, page 3. So here D equals to F. Oh, I think I've rubbed those things off. So the things I'll be needing: fxx, fyy, fyx. No. fxy, fyy. Alright. So the same thing, if D, so if D1 plus your fxx, if it is lesser than 0, so and your D2, which is equal to D, is greater than 0, so this is going to be strictly what? So it's going to be negative definite, and if you're having a strictly concave functional. So when we set up our Hamiltonian, we had 4x minus 5y squared and plus lambda into brackets. I think this was 8y, the state variable. So now the the x, which is written as the f of x, gives us 4 here. Then the h, okay, from here, let me just write it. Fxx is going to be equal to what? 0. So you differentiate 4 with respect to x, again is 0. And the same thing, when you differentiate 4 with respect to y, it's still going to be 0. So fxy to be 0, because what you have here is just 4. So if you try to do, there's no y. Alright. Now the other one, the h, the y, gave us minus 10y plus 8 lambda. But if you look for fyy, it's just going to be minus 10. You know how this appears. So when we set up our discriminants, we have under discriminant there. So what is this? Fxx, fxy, this minus 10. So d, the 1 is equal to 0. Fx is here, 0. Then d2 equals d. It gives us 0 times minus 10, 0, so everything is still 0. So when you have something like this, like the other class, what do? We reorder the discriminant. So d, we reorder the d matrix. So we have d being equal to minus 10, 0, 0, 0. So here, from here, d1 equals to minus 10, which is now lesser than 0, right? And then d2 equals d equals everything is 0. This time this 0 minus this 0. So if you look at it, both sides, from both sides, or for both sides, okay, or for both, just for both. So you have d1 being lesser or equal to 0, right? And d2 equals d, no, no, it doesn't have to, so greater or equal to 0. For both, d1 is lesser or equal to 0, and d2 is that. So the objective functional The objective functional is jointly concave. So that's just the change in conclusions. So when we're doing um, calculus observation, so this would have been simply um, concave. So instead of strictly, yeah, this would have been simply concave instead of strictly concave. This would have been simply, but this what we have is jointly concave in x and y. So you have to be careful with the conclusions. Okay, so and since the constraint is linear, so what was the constraint here? The state variable. Our constraint was 8y. Yeah, 8y. So which is linear, it's not reached by 2. So the constraint or 3. The constraint is linear. It's also it's also jointly it is also jointly concave and needs no testing. So I might say that you would have to familiarize yourself with the conclusions just as I am also trying to familiarize myself. Am I trying? I don't even know at this point. Alright, so let's just keep familiarizing ourselves with the different conclusions. You know, the conclusion of the Ishan, the conclusion of calculus of variation, the conclusion of optimal control theory questions. They are similar, but they are not the same. So like we all of us, including myself, kind of have to like be able to differentiate, you know, when to write the conclusion like this. But you have an idea in mind. When it is concave, it's concave for everything. When it is convex, it's convex for everything. All right. So yeah, that's it. I think we are done with this particular question. So the next thing is for us to um go into what do you call it? Um, an assignment. Okay. So if this had been um greater or equal to 0, so it would have been convex. All right. Instead of concave, it would have been convex. Yeah. So you may want to find out maybe as an assignment on the side, what if this was just greater than 0? What if it was just greater than 0? Not greater or equal to, just greater than 0. And I think I should mention something. If it is greater than 0, like you don't have to reorder. You don't have to reorder this matrix, the matrix of the D matrix. You don't have to reorder it. So from the first one, whatever you get. So let's say D1 here was 16. All right, if D1 was 16, so D1 greater than 0 and D2 equals D, greater than, 0 as well. So the objective function will be what and what and what and what and what. So you don't have to like do this kind of a thing again. You just do it once. If this were lesser than 0 as well, it's just once. Okay, so let's say minus 16. That means D1 is lesser than 0 and this still remains for everything. It's going to be greater than 0. So the objective functional, whatever. How do you conclude it? Okay, so like I said, an assignment. So there are two assignments on the board. So this is question 1. Maximize, upper bound 2, lower bound 0. So into bracket 6x minus 4y squared, then dt. Alright, then x dot equals, the constraint 16y subject to x0 and x2 equals 4 weights. The same thing here is just a longer 5x plus 3y minus 2y squared. Okay? So the constraint 6y, x0 equals 7, x1 is 7. So that's for the sufficiency conditions of both questions. So when you're done, so of course you'll be getting your state variable, co-state variable, your control variable. Okay, then along the line, the slope. So tell us what the slope is, and tell us what the sufficiency conditions. Okay, tell us, is it concave, convex, all of those things. So we'll see in the next class. There's still another class. I think maybe 1 or 2 more classes on optimal control theory before we beat this topic farewell. Thank you very much for watching. See you in the next video.